So hello friends, welcome to my MPLS training. Today our topic will be MPLS traffic engineering, right? So although it is a simple topic, not very complicated, but I definitely admit that there are certain complex issues related uh, to this particular application of MPLS, right? In fact, in my previous videos, I have already discussed about another very popular application on MPLS, that is MPLS VPN. Now, to carry out MPLS VPN, you don't have to do a lot of extra configurations, or you don't have to be 100% clear regarding certain other networking issues, right? In fact, we had worked with actually two main concepts. One is VRF. Uh, then inside for any particular VRF, we had the concept of route distinguisher, route target, and all. And we had some modifications in the routing protocols, namely the MPBGP part, right? We had to do with certain address families. So those are not at all very complicated and very easy to understand. And plus, you don't need too much of knowledge regarding some unknown areas of networking, right? But for traffic engineering, it is somewhat a different story, where you will come across some new terms. Maybe these are new terms for some candidates, because as far as my knowledge goes, these are not taught into traditional networking courses, right? For example, you will come across a name CSPF, you will come across a name RSVP, right? And as we will be working with mainly bandwidth issues, because traffic engineering is targeted for bandwidth management mainly. So for that reason, uh, we will also deal with certain areas which are related to bandwidth management, right? So at the very beginning, I would like to declare that there will be certain terms and certain elements of networking with which you people may not be familiar with, but that won't be any difficult issue, because in my theoretical class, that is in today's class itself, I will clear out uh, the relevant and necessary queries regarding all these new areas, right? Because if you are considering these new areas, then they can be uh, specific separate chapters, right? So no need to talk too much about them in an in-depth fashion. I will just make clear the main uh, areas of those items which are related to this traffic engineering part, right? So let us start. And in today's video, you will not get any practical. This is entirely a theoretical video, and uh, it may be a prolonged one, right? It may be a lengthy video. So before starting, I request all of your patience and cooperation, because this lengthy discussion is needed when we will be going for the traffic engineering practicals. Then we need to be 100% clear regarding certain issues. So those certain issues will be clear in today's lecture. So please be patient. I request all of you. Okay, so let us start with the MPLS traffic engineering theoretical video. So first of all, what is the definition? The definition goes like this: traffic engineering is the process of manipulation of traffic to fit the network. It is the art of moving traffic around so that traffic from congested link is moved automatically on an underutilized link. So if you see the next picture, say for example, uh, these 4 routers, they are connected in a chain-like fashion, and we have 2 sets of connectivity, right? Between each router, we have 2 sets of connections. One is denoted by this green line, another one denoted by this blue line. Now, as for this green line, I have written best path according to IGP and by default utilized. Whereas for this blue one, it is not the best path according to IGP, so not utilized, but can be utilized using MPLS TE. Right. So there may be paths which are uh, best path and which are not so best path. Right. And if you are not going by static route configuration, if you are going for routing protocols, we will see that routing protocols have their own logic to select the best path, right? And we cannot manipulate them in their logic for selection of the best path, right? If we are at least sticking to their defaults, right? Now, if we are going by static route, then we can use both these best and not so best paths, right? But when we are going by the IGP or by the routing protocol, then definitely the routing protocol has certain logics by which it always selects the best path, and whenever any traffic needs to be delivered, those traffic will be put into that best path, right? If that best path fails, then definitely the not so best paths will be uh, called into action, right? Now, what happens due to this? Due to this, you will see the best path will, you will come across situations when the best path will be overutilized, right? Where uh, it will very easily come to a point of bandwidth crisis when all the data are pushed through that best path, right? But we are having a not so best path which is remaining underutilized, that is not at all being utilized. Why? Because the routing protocol is not considering it for the time being, right? So in that case, although we are having other alternative paths, we are faced with the issue of bandwidth crisis. Now, any kind of traffic engineering is to address that issue. That is to use the not so best paths, that is the underutilized paths, so that bandwidth crisis doesn't happen, and uh, all the existing paths for a particular destination can be utilized. Maybe their utilization can be proportionate utilization, that is a greater load of traffic is carried by the best path, whereas a lesser load of traffic is carried by the not so best path, but still we are utilizing that not so best path, right? Now if we are using static route, it can be done, but definitely you all of you understand that in a typical enterprise topology, it is very difficult to use only static route, right? In fact, it is impossible to manage everything with static routes. So we are left with the mercy, left at the mercy of the routing protocols. Now, if you are considering routing protocols, then you can have policy-based routing. Now, in case of policy-based routing, there, although you can use the underutilized paths, but still it will lead to certain complications, right? And it is mainly based on the destination. For any kind of policy-based routing, we are actually making the policies, we are formulating the policies for using the not so best paths, keeping in mind the destination where the source doesn't play any role, right? And if you are using a routing protocol like EIGRP, which has a concept of variance, now using the variance value, you can use the not so best paths to perform an unequal cost load balancing using EIGRP, right? But at the same time, that particular concept using EIGRP is not very simple. It is also having its complications, and moreover, you cannot rely on EIGRP because that is a Cisco proprietary protocol, and in today's networking topologies, you will hardly find any topology which is using entirely a Cisco network, right? You will come across several vendors' devices. So for that reason, it is not, you will seldom find EIGRP in every place. So forget about using EIGRP to use the not so best paths using its variance method, right? Now, in this particular situation, MPLS comes to our rescue, right? So MPLS can be utilized very easily just by some very user-friendly commands. You can use MPLS to perform a traffic engineering, and that traffic engineering not only concerns the destination, it also concerns the source, which we will see. When we'll be going through the practicals, it will be even clearer to us that MPLSTE is more concerned about source. So here it is telling that not so best path according to IGP, so not utilized, but can be utilized using MPLSTE. Now, if TE is done by MPLS, then it is implemented by the head end or the source of the traffic, in contrast to the destination based TE as done by IP policy based routing. I was just discussing this issue a little while ago, that in case of PBR or policy based routing, whenever you are going for a traffic engineering, it is mainly destination based, whereas in case of MPLS traffic engineering, it is based on source. So that means the network administrator has a greater control on the uh, traffic engineering jobs, right? Now it is to be noted that T can be performed by EIGRP, unequal cost load balancing, but it lacks the sophistication, scalability and robustness of MPLS-TE. For MPLS-TE, any link state IGP like OSPF or ISIS is a mandate. Now this is an important thing, that if you are once again visiting this diagram, the routing protocol that will be working here must be always a link state routing protocol. It should not be any distance vector or path vector, something like that, right? Why link state protocol? Because uh, in case of traffic engineering, we are actually concerned about bandwidth, prices and management, right? For this reason, the routers should be 100% aware of the bandwidth conditions throughout the entire topology. Now that kind of awareness can be created inside the routers if you are going for a link state protocol, because only a link state protocol will have uh, topology, topology table which will be not present in case of any kind of distance vector or path vector protocol, right? So for that reason, a link state protocol knows a particular topology from top to bottom. That means from beginning to end, it knows about the different sections of the what are the bandwidth conditions for the different sections of the topology, and accordingly they can modify themselves whenever those bandwidth issues become different. If a particular bandwidth falls, then immediately a link state protocol can adjust its uh, routing table according to its best route algorithm, right? And to put it in very simple words, if you are considering the link state protocols, they are primarily concerned about bandwidth, isn't it? So for that reason, we are utilizing it for manipulating an issue which is also a bandwidth issue, that is traffic engineering issue, right? So whenever you will be doing a traffic engineering, you will find that inside the IGP will be working, will be either OSPF or ISIS, right? Now MPLS operation in a MPLS TE operation in a nutshell. First, I will read out all these 7 points. Then I will explain the important areas, and already I have highlighted them in bold fonts. So you see, number 1 point, link state IGP at first floods the bandwidth, cost, etc. of the different links of the domain. Then CSPA for constrained shortest path first, then decides the nodes and links on which the TE path can be constructed. Then resource reservation protocol or Rsvp sets up the TE path. It is actually an end-to-end level switched path between a head end or the source and tail or destination. The two ends of the TE path are marked by tunnel interfaces. The tunnel interfaces are announced by the link state IGP by autoroute process or inserted manually in the routing table. All destinations behind the tail of the TE path must be reachable through that path using the tunnel interfaces. A very important thing to note, this TE path is not like an enclosed, encrypted path passing through the original IGP path like a VPN. It is actually a certain portion of the original IGP path that is guaranteed to enjoy a particular bandwidth from end to end. If a VPN is considered as an opaque tunnel, then TE path can be considered as a transparent tunnel where every traffic inside it is visible. VPN can ensure traffic protection, whereas TE path can ensure bandwidth protection. Right. So let us visit this picture. Now, this picture here, R1, R2, R3, and R3, R4, and R5, they are entirely under the domain of a particular link state IGP, right? So this entire domain, the space that is confined between these two green dotted lines, these are this entire space, they represent a particular link state IGP domain, right? And you can have several links, physical links working in between, right? You can have 10 physical links between R1 and R2, 20 physical links between R2 and R3, 5 physical links between R3 and R4, then say again 10 physical links between R4 and R5, and so on, right? I'm not concerned about the physical links. So I have bundled all the physical links and presented them as a particular link state IGP domain whose boundaries are marked by these two green dotted lines, right? Now this red line, I should have drawn it across through these routers. Anyway, forget that issue. These red lines, do not confuse them to be physical links. Once again, I repeat, I haven't drawn these red lines to represent physical links between these routers. They are not fast Ethernet links, not serial links, not any kind of fiber optic links, nothing. They represent a path, a logical something which is a path, and that is an MPLS TE path. Right. So this is an entire logical thing which we consider as the MPLS TE path. Once again, do not confuse them with physical links. Right. Now, how is this path constructed? This virtual logical path, how is it constructed? So at first, there are certain steps. So what are the steps? Once again, I visit this operation. So link state IGP at first floods the bandwidth, cost, etc. of the different links of the domain. So at first, we have already told that these two green lines, they represent the link state IGP domain. So inside this domain, the IGP floods all the bandwidth conditions of the different physical links, of the cost conditions, because already you know, in case of OSPF, OSPF is concerned about cost definitely, but if you are leaving OSPF on its default, then it considers bandwidth to calculate its cost. Otherwise, you can also specify some administrative cost also. Anyway, so these bandwidth and cost issues, according present in all these physical links, these are distributed among all these routers, right? So that means this R1, R2, R3, R4 and R5, they at first become aware of all the bandwidth and cost conditions of the different physical links that are connected, that are connecting them, right? After that, CSPF, or constrained shortest path first, this decides the nodes and links on which the TE path can be constructed, right? Now CSPF is nothing but an algorithm, right? Whenever you have learned about OSPF, in fact, that name OSPF is due to the name of the algorithm, which is shortest path first, right? And by appending a particular, or rather by adding a particular word open, we get the name of the protocol, open shortest path first, or OSPF. Now, OSPF is nothing but an algorithm, right? In the same way, CSPF, or constrained SPF, is also an algorithm. I'll be telling something about that algorithm, the specialty of that algorithm, a little bit later, right? When I'll be moving into the notes on CSPF. Now, CSPF, what it does, it actually now informs that IGP that see, you can construct this path by using certain physical links and certain nodes, right? That means certain routers, right? Once again, I repeat, after IGP collects all the bandwidth and cost for that are present in the different links inside that IGP domain, it hands those informations to the CSPF algorithm, right? Now, CSPF algorithm, it will now inform that particular IGP that these are the different physical links and these are the different physical nodes through which a particular virtual path can be created for traffic engineering. Understood? Now what happens? Then another protocol comes into action, or whose name is a very strange, whose name is good, no doubt. It's a simple name, Resource Reservation Protocol, but it uses a rather strange acronym. According to its full form, it should have been RRP, but here they are using Rsvp, right? So Rsvp sets up the TE path. It's actually an end-to-end level switched path between the head end and the tail. So after CSPF specifies that these are the links and these are the physical nodes and links through which a TE path can be created, the job of establishing that TE path or this virtual path now entirely falls on Rsvp, right? So Rsvp now constructs that path. How that path is constructed, it is nothing but reserving a portion of the bandwidth, right? If the total bandwidth is say 100 Mbps, then Rsvp will reserve, for example, say 40 Mbps or 50 Mbps, which will not be given to anyone else, right? And that reserved end-to-end path will be a traffic engineering path, right? The two ends of the traffic engineering path are marked by tunnel interface. Now, the traffic engineering path is initiated by this node, right? And this particular node will be considered as the head end or the beginning of the path, and where the traffic engineering path gets terminated will be considered as a tail end, right? So the TE path actually is connectivity, a direct connectivity, a logical direct connectivity definitely from the head end to the tail end device, right? And this logical or virtual path is actually uh, having no physical interface, right? As it is a virtual path, then definitely it should not be, we can expect that it should not be working directly on any physical interface. So, but it must have any interface to work, because what is an interface? An interface is basically a doorway, right? Whenever we want to use a particular link, be it a virtual link or be it a physical link, the doorway or the gateway is actually called the interface, right? I think you people already know this. So here, the role of the interfaces for this virtual path is played by certain virtual entities which are called tunnel interfaces. So here is a tunnel interface and there is also a tunnel interface, right? But don't think that this tunnel is an enclosed or encrypted or encapsulated tunnel like a VPN tunnel. It is nothing but a allotted bandwidth, end-to-end bandwidth, right? So whenever you see this tunnel, don't consider it as an encapsulated or encrypted pathway. You should consider it as a pathway that can guarantee bandwidth and nothing else. No security, no encapsulation, no encryption, nothing else. But it can definitely guarantee a bandwidth, right? If you are creating this tunnel path using 10 Mbps, then you are always there to enjoy 10 Mbps. Nothing more than that, nothing less than that, right? The tunnel interfaces are announced by link state IGP by the auto route process or inserted manually in the routing table. Now, if the routers are to use this tunnel path, then definitely the tunnel interfaces at the head end and at the tail end must be inserted into their routing table. Otherwise, how come they know that this is an interface through which I need to push the data into the TE path, right? So just like any other fast Ethernet or serial interface, those interface needs to be put into the routing table also, so that the routers, the tail end and the head end, they have an idea how to use that tunnel path, right? Now that can be done by IGP. They use a method, the link state IGPs, they use a method known as auto route method, or you can manually uh, add those interfaces in the respective routing tables of the head end and the tail end routers, right? But before that, that is, unless and until those tunnel interfaces are incorporated into the routing tables, these routers will don't have any clue, right, how to use the MPLS TE path. All destinations behind the tail of the TE path must be reachable through that path using the tunnel interface. That must be, isn't it? Because you are creating this MPLS TE path for the sake of traffic engineering. So for that reason, all destinations which are beyond this tunnel or beyond this TE path must be reachable via this TE path, right? At least you should be rather forcing your routers so that they always use, or they will at least use this TE path or this tunnel path to reach the destinations which are beyond the tunnel head end, sorry, tunnel tail end, right? Very important to note. This TE path, in fact, I was just discussing it a little while ago. Once again, I read this paragraph. This TE path is not like an enclosed encrypted path passing through the original IGP path like a VPN. What happens in case of a VPN? In case of a VPN, uh, if you give a trace route from the source to destination, you will see a direct hop, right? Whoever have done my MPLS VPN class, you have seen that whenever I am giving a trace route, it is a direct hop from the source to the destination, right? The in-between hops are not available if we are following the VPN route, right? Why it is not available? Why those intermediate hops are not available? Because that VPN path uses two technologies called encapsulation and encryption. Now, forget about encryption because that will give confidentiality to your data, but your data is actually shrouded from the intermediate hops by using some encapsulation technique, right? So in that way, if you are considering a VPN, you can consider it as a closed tunnel path, right? A covered tunnel path that goes through the IGP domain. That is, if this happens to be a VPN, this red line, then you can consider it as an opaque path through the IGP domain. The rest of the IGP domain will not be able to see what is going through this VPN path. But if you are considering a TE path, then definitely all of them will be able to see that, right? And you will see the next hops also. Whenever you will be using the MPLS TE path, you will also get the next hops, right? So how is this possible? This is only possible because this particular path is not at all built on the basis of encapsulation, right? It is nothing but allotted bandwidth. The data which are being pushed in this path, they are always guaranteed to enjoy a particular bandwidth, right? They will never come across any bandwidth crisis issue. Understood? So this is the difference between VPN and MPLS path. So here it is telling that it is actually a certain portion of the original IGP path that is guaranteed to enjoy a particular bandwidth from end to end. If a VPN is considered as an opaque tunnel, that is a tunnel which is shrouded from the rest of the IGP domain, then T path can be considered as a transparent tunnel. The entire IGP domain can see what is going through that T path, where every traffic inside it is visible. VPN can ensure traffic protection. This protection is basically protection from hackers, right? Protections from those entities who are actually eavesdropping into your network, right? They are not your actual destinations. So if you want to ensure their security, then that security protection is ensured by this VPN, whereas TE path can ensure bandwidth protection. I hope it is 100% clear. Now let us move to the other issues. First, how CSPF decides the path. Now, it is telling CSPF is only interested to find out the best path only for the endpoint of an LSP path and not for all destinations, as traditional SPF does. It considers factors like link cost, link bandwidth, link attributes, administrative weights, etc. to decide the best path. For content, okay. So let us discuss this a little bit later. First, I'll clear out the definition. So, why the term C or why the term constrained? Constrained means it is somewhat limited. Its scope is somewhat limited. Why it is limited? Because If you consider a traditional OSPF or any other or ISIS, that is any other protocol which is using traditional SPF. Now, traditional SPF will find out the paths for all the destinations, right? Not for any specific destination. That is not for the tail end. In this case, our specific destination is the tail end. Whereas CSPF is only interested about the tail end. So that's why it will definitely follow the logic that is used by traditional SPF. That is, it will be considered those issues like bandwidth and administrative cost and so on. But at the same time, the paths which are directed by it, which will be prescribed by it, will not be every possible path of the IGP domain, right? It will be simply a path that goes to the tail end, right? So it is only interested to find out the path, to prescribe a path to reach the tail end, not for all destinations. So that's why the term constrained has been inserted here, right? So it is having a C in front of it. Now for contending paths, that is if CSPF is coming across several paths, all of which can be considered as good paths for reaching the tail end. In that case, what it will do, because SPF in that place will be working in some other logic, traditional SPF. So what it will do? So it has the following tie-breaking logic, and that tie-breaking logic will be followed exactly in this sequence. So at first, it prefers the path with the largest minimum available bandwidth. Largest minimum available bandwidth. If we consider, just for the sake of our discussion, let us consider these are two paths which have come in the hands of CSPF, right? Now, this green path has a minimum bandwidth of 100 Mbps, or rather say 50 Mbps, and this blue path has a minimum bandwidth of 75 Mbps. Now, in that case, CSPF will always consider this blue path, not the green path, right? Why? Because the blue path has a better minimum bandwidth. It has a better minimum bandwidth, right? It has a higher minimum bandwidth. So the first logic is always go for that path, always point out to that path which has the minimum, the maximum, the highest minimum bandwidth. Then if all the paths they do have the same type of minimum available bandwidth, then definitely once again a tie breaking needs to be done. So in that case, it prefers a path with the lowest hop count. So now suppose this green path and blue path, they all have the highest minimum bandwidth of say 50 Mbps. So in that way, it cannot differentiate between them. Now, if it sees that this green path passes through R1, R2, R4 and R5 and not touching R3, whereas this blue path touches all 5 routers, then definitely the green path will be having less number of hops. So in that case, it will prefer that path with less number of hops. And if in that way also it cannot differentiate between the contending paths, in that case it goes for a random pickup. Now that random pickup always picks up the first available path. That means the path with which it has first become acquainted. So once again, if this blue path has come in the hands of CSPF at first, and then this green path has appeared, and both of them have similar attributes, in that case that blue path will be used and that green path will not be used. Why? Because the blue path has made itself available at first in the hands of CSPF. Understood? So in this way CSPF works. CSPF also takes care to decide any new better paths if available. This is path reoptimization, and it is decided in any one of the four methods. It can be a periodic reoptimization after every 3600 seconds. It can be a manual reoptimization. It can be an event-driven reoptimization. That means as soon as any link change happens. And it can be even a no reoptimization, which is technically called lockdown. Right. So as CSPF has SPF inside its genes, inside its bloodstream, so definitely it will be always eager to find out if any other new path is coming up with better attributes, isn't it? It is always eager, always on the lookout, just like a traditional SPF. Now, this particular attitude, that is once again a new path is available, then go for that path, forget about the previous path which is not so good. This particular property of CSPF is called its reoptimization property or reoptimization method. And this reoptimization method, it can be done in four ways, right? So it can be a periodic reoptimization. That means after every 1 hour it scans, right? It does a scan, and if it finds a better path, it will immediately accept it, leaving out the previous not so better path. It can be a manual reoptimization. Suppose if the administrator by force wants CSPF to accept a path as a better path, maybe according to the logic of CSPF that is not a better path, but the administrator is coaxing CSPF to accept that not so better path as a better path. In that case, it will always be a manual reoptimization. Now, event-driven reoptimization, as soon as any link change happens, in fact, this is the most, the most obvious one, where whenever any change in the link happens, definitely CSPF will be ready, will start its work to find out that new path, to establish that new path and forget the previous path, right? So that is event-driven reoptimization. And then finally, if we are forcing, once again the network administrator is forcing CSPF not to go for any other better path, even if that is available. So in that case, it is technically called a lockdown. Understood? Okay. Now, what is actually a TE path? We have already understood that TE path is nothing but a portion of the IGP domain which has a guaranteed bandwidth, right? Now, definitely that portion of the IGP domain should be having certain entities. That virtual path should be touching certain entities. It should not be hanging in the air, isn't it? So what is it actually? A physical path, if you consider a physical path will be consisting of certain links and certain nodes. In the same way, a logical path must be also concerned around certain links and certain nodes. So what are those links and nodes? So what is actually a TE path? The path in reality connects different links and nodes, and these components are called explicit root objects or ERO. So every path is basically a string of ERO. ERO can be provided by the link state IGP or manually. In the first case, the path is a dynamic path, while in the latter case, it is an explicit path. The ERO can be strict or loose. In case of a strict ERO, the different root objects are consecutive, like a string consisting of all the bits. In case of loose ERO, the root objects are not consecutive, just like a string with some intermediate bits missing. Right. So, if you once again consider this TE path, although this I have told you beforehand that don't consider this red line to be physical link, right? It is not at all a fast Ethernet link or serial link or something like that. But definitely it is passing through any kind of physical link, isn't it? It is not hanging in the air. So that means this MPLS TE path will be consisting of some physical components. And what are those physical components? Certain physical links and definitely certain routers. Now these routers which belong to this paths, these are called explicit root objects. Explicit root objects or ERO. Now you may hand over the responsibility of finding out the ERO in the hands of the IGP, right? The IGP will find out through which ERO or through which objects or routers this TE path will be passing. Otherwise, you can manually specify the root objects or the routers through which the path will be passing, right? Now, if you are putting it in the hands of IGP, then in that case, that ERO, that means that string of root objects, that will be considered as a dynamic ERO. And if you are specifying the root objects by yourself, it will be called a explicit ERO, right? And a very interesting thing can happen. You can even have a strict or loose ERO. In case of a strict ERO, you will be getting a list of ERO like this: R1, R2, R3, R4 and R5. That is, we are not leaving out any intermediate root object. So if a particular TE path is constructed without leaving out any intermediate root object, then that string or ERO is called a strict ERO, right? And if we are leaving out certain root objects, that is, when we are building this MPLS TE path, we are defining this MPLS TE path, we specify R1, R2, and then jump to R5, leaving out R3 and R4. In that case, that ERO will be called a loose ERO. It will not be a strict ERO, it will be a loose ERO, right? Now, how to find out that loose ERO, that we will, how to work with a loose ERO, because you might have a question coming up that if we are leaving out these two root objects, then how come the TE path gets complete? It will be immediately broken here. No, it will not be broken here, because to find out these two is once again on certain other aspects. So that we will come across when we will be doing the practical part, right? Because the secret lies in the coding. Now, so I think you have understood this statement that a strict ERO, what is a strict ERO? You can consider a strict ERO as a string consisting of all the bits, just like a string which has all the bits, no bits missing. And in case of a loose ERO, certain bits have fallen down, right? So that is a loose ERO. Now every path has a path option value to specify its unique numerical identity. This path option value does not decide whether this path can supersede another path, but multiple paths originate from the same tunnel interface. But if multiple paths originate from the same tunnel interface, I have this typing error on my part, I have dropped that if. So always consider an if here. So, but if multiple paths originate from the same tunnel interface, then the sequence of declaration of the paths actually decides which path is preferred. Path declared first is more preferred. Every explicit path also has a name. Now, whenever we are constructing an MPLSTE path, it must have two parameters. It must have a path option and a path name, right? Now, path name and path option, you have already understood that these are two identification. One is a numerical identification for that path. Another one is a named identification. Now, this numerical identification has nothing to do with its preference, because, for example, if we are declaring these two paths, let us suppose that these are two MPLSTE paths, and they have originated from the same tunnel interface, right? Here is a single tunnel interface, and from the single tunnel interface we are creating two tunnel paths, right? Now, in that case, if this green path is declared first and it has got a path option of 5, and then we have declared this blue path with a path option of 1, that means a lower value, don't consider that this blue path will be considered at first, right? Don't think like that. The path which has been declared at first, maybe it is declared with a higher value, path option value, but still, as it has been declared before this blue path, and as they are originating from the same tunnel, in that case, the green path will be declared, right? Will be preferred, right? So path option has got nothing to do with the preference. It is simply a numerical identity for the path. But the priority for any particular path as to this, I am having this path and this path. So with which particular path to be used? So every path has a bandwidth value and a priority value. Bandwidth value must be comfortably within the specified bandwidth value at the interface for Rsvp. The priority value can be set up priority to decide if this path can preempt another existing path, and hold priority to decide if another path can preempt this path. And both values ranges between 0 to 7, where 0 is best and 7 is worst. So, if once again we have two paths, a green path and a blue path, and if we want the blue path to be having a higher priority than the green path, then definitely we should be working with the priority value of the two paths, right? Now, all the MPLSTE paths, they do have two types of priorities. One is a setup priority, another one is a hold priority. The setup priority, it is to decide whether, if you are considering this green path, so if we are specifying a setup priority of this green path, better setup priority for this green path than this, of this blue path than this green path, in that case, it will always preempt this. Let me present you with a topology, with a test case scenario. Suppose we have declared the green path first with a setup priority of say 5. Now we declare the blue path, right, with a setup priority of 10. In that case, as the green path has a lower priority and lower priority is more preferred, so it will be always preferred. But if I have declared this blue path with a priority value of say 2, that means its setup priority is lower, is a lower value than the setup priority of this green path. In that case, this blue path will be a preferred one, right? even if it is declared later. So once again I present this scenario. We declare the green path first, the blue path later on. The green path comes with a setup priority value of 6 and the blue path comes with a setup priority value of say 3. Now as it is having a lower setup priority value, in that case it will automatically preempt, that is it will push down the green path and become the more preferred path, right? So this setup priority specifies whether this particular path has the capability of pushing down some other paths. And hold priority, because I have mentioned already that priority can be of two types, setup priority and hold priority. Now hold priority will decide whether this path will be suppressed by some other paths. So one is to specify whether it can suppress any other path, and the second one, that is the hold priority, is to specify whether this particular path in question will be suppressed. It will be suppressed by some other paths. Understood? So whether a particular path will become preferred or not, that depends upon its priority value, not on its path option value. Right? Its setup priority and hold priority will decide whether this path will be the supreme path or not. And these priority values, both setup priority and hold priority, they will their value ranges from 0 to 7, where 0 is the best and 7 is the worst. That is, lower the value, the higher the priority. In fact, this kind of a treatment we have already seen. If you remember those lessons of spanning tree protocol, right? So in case of spanning tree protocol, we have seen that the lower values, right? The lower values, they get more preference. Here also the same thing happens. The lower value gets more preference. So till now we have discussed how CSPF, we have actually discussed two steps. So at first IGP will flood the different bandwidth conditions and cost conditions of the entire IGP domain, and these informations are taken up by CSPF. Now CSPF will decide, or rather prescribe, certain ERO or explicit root objects through which a particular path can be made, right? Now the actual path needs to be established. So that definitely is not done by CSPF or IGP. It is actually done by Rsvp, right? So if you consider IGP as the information gatherer, CSPF as the design engineer, then Rsvp is actually the site engineer, right? Who is building the path, isn't it? So how Rsvp consolidates the path? After CSPF has decided the path, Rsvp reserves the path bandwidth and actually sets up the path. So it is actually the site engineer. To be noted, Rsvp allocates the path bandwidth in an end-to-end fashion, and it will refuse to do so if any section of the decided path is not adhering strictly to the bandwidth mandates. Now, if you people have gone through any study on quality of service or QoS, you may have come across Rsvp, right? And what was the context of Rsvp? It was actually when the QoS path is rather built in the int serve model, not in the diff serve model, right? So in case of int serve model, Rsvp is called. Why? Because Rsvp is something which always works in an end-to-end fashion. So this is a site engineer who is always interested to work from one end to the other end, right? He will not be, this particular site engineer will not be satisfied if you are giving it certain small sections to work with, right? It always needs the entire domain under its jurisdiction. And to specify, uh, to, uh, to, to be sure that whether this entire domain will come under my jurisdiction, Rsvp will first test the available bandwidth, right? Because this is very simple to understand. What is an MPLS TE path? It is nothing but a section of the IGP domain that is uh, created that is created for enjoying a particular bandwidth, right? So Rsvp will be primarily interested for bandwidth issue, and it will definitely check whether the required bandwidth is available from beginning to end, right? So it is a very strict site engineer. So that's why, to be noted, Rsvp allocates the path bandwidth in an end-to-end fashion, and it will refuse to do so if any section of the decided path is not adhering strictly to the bandwidth mandates. Suppose I put a mandate on the bandwidth that the path should be always enjoying a 50 Mbps bandwidth, right? Now Rsvp sees that here it is 50 Mbps, here it is 50 Mbps, but here it is 49 Mbps. Once again, here it is 50 Mbps. Rsvp will simply stop working. Even it is 49.5, 49.9 Mbps, no. It must be 50 Mbps because that is the bandwidth policy for creating my MPLS path, and I must be strictly adhering to this policy because I am the site engineer. And if I fail, if I leave some loopholes, then definitely no one will be held responsible apart from me. Human beings can tend to make this kind of mistakes, but protocols and algorithms, as you know, they are very mechanical and they are very logical. They will definitely not go for any kind of shortcuts. So Rsvp, our site engineer, it always makes sure that the uh, all the sections which are participating inside this T path, they are strictly adhering to the bandwidth requirements. Okay, now how Rsvp works? It uses certain messagings, right? So what are the messages? The messages are path, RESV, that means reserve, then path tier, RESV tier, and RESV tier conf, right? So let us discuss these one by one. So at first, the path, when Rsvp is actually setting up the path, it is the site engineer is actually manufacturing that path from the head to the tail end. So this path is basically a request for bandwidth message will be granted and forwarded if the requested bandwidth is available. So Rsvp will send a path message from R1 to R2, and this path message will be asking R2, can you ensure me a path having say 50 Mbps? So it is a question that R1 asks R2, can you ensure me a path having 50 Mbps? Now this answer is not promptly provided, right? This R2 will not promptly provide with a yes, because if it is done in that way, then R1 becomes very confident and it becomes least bothered, and it actually develops an idea that yes, I have a path where I will be enjoying a 50 Mbps bandwidth. But suppose just between R2 and R3, if the bandwidth falls at 20 Mbps, then definitely the path will break, the TE path will break. So for that reason, R2 will not give a prompt reply, even if it has 50 Mbps. What it does, it hands over this message to R3. Can you ensure me a path of 50 Mbps? R3 in its turn hands over the message to R4. R4 in its turn hands over the message to the tail end, that is R5. And R5 is the destination of the tail end, right? Now R5, when it sees that yes, I have 50 Mbps here, it replies back with a reserved message. So reserved message is nothing but confirmation and reservation of messages, of bandwidth messages. So R5 assures R4 that yes, I am reserving reserving a 50 Mbps bandwidth for you. Now R4 assures R3 regarding that reservation. R3 assures that reservation to R2, and then finally R2 assures that reservation to R1. So what is the final outcome of all this process? The final outcome is it is 100% assured that there is a 50 Mbps path between R1 and R5. There is no wrong values or nothing wrong inside it. It is a guaranteed 50 Mbps path from the head to the tail end, right? To be noted, when we configure bandwidth for Rsvp, we specify two values. This you will come across in the configuration part, but in that when we'll be doing the configuration, then I will definitely come up with this issue. But first, at the first place, I'll also clear out this issue right now. The first value is the total reservable bandwidth in kbps at the interface, and the second value is maximum bandwidth per flow in kbps at the interface. If no specific bandwidth is not made, if no specific, here I have mentioned two no's. It should be either if specific bandwidth is not mentioned, or it should be if no specific bandwidth is mentioned. Anyway, forget about these typing errors. So just think that I have wished to tell here that if no specific bandwidth is mentioned, then Rsvp considers it to be 75% of the interface bandwidth, and if the bandwidth statement is dropped altogether, then Rsvp considers zero bandwidth has been reserved. So whenever you'll be configuring Rsvp in the routers, you will see, specifically in the router interfaces, physical interfaces, you will see that you have to put two bandwidth values, IP Rsvp bandwidth and then some value, then some value. Now say I am putting IP Rsvp bandwidth 75, then 25, right? Now the first value, another thing, this 75 and 25, their units are in kbps, mind this. So Rsvp values are provided, the bandwidth values are provided in kbps. Now the first bandwidth value is actually the portion of bandwidth that we want as a guaranteed bandwidth from the physical interface. For example, if the physical interface is a 100 Mbps interface, and if I am specifying there 75, so that means 75 kbps is preserved, right? It is preserved entirely for the MPLS TE path and not for anything else, right? The next 25 kbps is actually what bandwidth will be available per flow. Yes, we have reserved certain bandwidth. Now, whenever any single data flows, how much what is the maximum bandwidth that it can consume? Out of this 75 kbps, what is the maximum bandwidth that it can consume? So that is, say, 25 kbps. So these two values, one is the total reserved bandwidth of the interface, that is entirely dedicated for the MPLSTE path. And the second bandwidth is actually the maximum bandwidth that a single piece of data can use from that reserved bandwidth. Understood? Now here, if we just specify the statement as IP RSVP bandwidth and leave it like that. Inside the interface, we put the command as IP RSVP bandwidth and leave it like that without mentioning any values, bandwidth values. So what happens then? RSVP understands that I have to reserve 75% of the available interface bandwidth. So if my interface is a 1 Gbps interface, then RSVP will be reserving 750 Mbps for it, right? 75% bandwidth. And if I am dropping the bandwidth statement altogether, then that means RSVP will not preserving any bandwidth. So be very, very careful regarding the RSVP bandwidth statements, right? Because whenever you are putting the statements, you must be putting it with all the parameters, necessary parameters, and at the same time you must be careful about the interface bandwidth. You should not be specifying any value which is higher than the interface bandwidth, right? Because in that case, as that particular bandwidth, say for example the interface is 100 Mbps and you have specified the RSVP bandwidth, reserve bandwidth to be say 200 Mbps, then definitely that MPLSTE tunnel will not come up, right? Because RSVP will fail to preserve that amount of bandwidth from 100 Mbps interface. So this is all about path setup, how the path is set up. Now the path maintenance. It is same as the path setup. It is done periodically after every 30 seconds, and 4 outstanding path messages will consider a reservation to be done. To be down. So what does that specify? When it is a question of path maintenance, it is done periodically after every 30 seconds, right? Don't think it is a path, don't confuse it for path reoptimization, right? We have already discussed something regarding path reoptimization, which is whose default value for periodic reoptimization is 3600 seconds, that is 1 hour. Now this path reoptimization, it is in the hands of CSPF. It is not in the hands of RSVP, because RSVP is not having the task to decide the path. It is not the design engineer, it is actually the site engineer. So its task is to construct the path. Now after constructing the path, it is also the maintenance engineer. Now that maintenance task will be done after every 30 seconds. How that maintenance is carried on? Exactly by the same set of messages. So after every 30 seconds, RSVP will be sending this path, and it will be reciprocated back or replied back with RESV, right? And if RSVP sees that I have sent 4 consecutive path statements and I haven't received any single RESV, then RSVP considers that something is wrong. So let us tear down this path, right? So the site engineer gets angry at that point that no certain particular section of the path is having some hiccups. So let us stop the path and do the necessary rectifications. Go there, do the necessary rectifications, and then once again come up with the path, right? Now, how the path tear down or path breaking down occurs. So it is done by using these 3 messages: path tear, request to tear the existing reservation, RESV tear, confirmation for reservation tear down, and then RESV tear conf, that is only for Cisco. So now if RSVP becomes angry because say a certain section of the path it is not responding back with that RESV message, right? So RSVP understands that something now needs to be done to rectify that error. So first I need to tear down the path. So how to tear down? It is once again a path tear message from R1 and R2, which is handed over from R2 to R3, that is handed over from R3 to R4, and finally handed over from R4 to R5, that is the tail end. Now the tail end replies back. It first tears down. It tears down the reservation and then replies back with a reservation tier. Then R4 tears down its reservation and replies back with RESV tier. In the same way R3 does, and finally R2 tears down the reservation and replies back to R1 with RESV tier message. Now, if you are using Juniper routers or any other vendor routers, the process stops at the second step. But if you are using Cisco routers, an additional third step is there where R1 will be sending a confirmation for reservation tier. That confirmation will be handed over in that same chain-like fashion up to the tail end or R5, right? Error signaling, right? Now, in this case, it can be a path error or it can be a reservation error, right? Now, path error, when path error can happen, message if bandwidth for the path message is not available, and reservation error is message if bandwidth as granted by RESV message is not available, right? Now, suppose when this R1, it wants to establish a path. So it first sends a path message to R2, and that path message definitely takes that question that can you ensure me a path of 50 Mbps? Now if R2 has 50 Mbps, then definitely it can reply back. But if it is lacking a 50 Mbps path, then it replies back. If suppose here it is not seeing a 50 Mbps path here, so it will reply back with a path error message, right? So without waiting for any further transferring of this path message, because there is no point in transferring this path message, because if it sees that I am not having a 50 Mbps here, so what's the use of handing over this path message to R3? So immediately when it sees that I cannot ensure the path which is demanded by RSVP, it sends a path error message, right? So that is the error signaling, right? And when RESV error occurs, suppose this R3, this R2 has developed a path with R3, and that path is a 50 Mbps path, right? Now suddenly R3 understands that on this side, maybe there is R4 or something like that. On this side, the bandwidth has gone down. The bandwidth is not 50 Mbps path, right? So definitely R3 will now instruct R2 to tear the reservation, right? So it will send a reservation RESV message here, right? And no, I'm telling it from the other way. Say for example, this R3 router, it sends a RESV message to R2. It is demanding it is telling R2 that I have reserved a 50 Mbps bandwidth for you. And if R2 discovers, it can be also R4 on this side, but as I am not having the drawing on this side, so it will be easier for you to understand if I consider it from the point of view of R2. Don't think that this message, this RESV and RESV error, this will not happen if something happens on this side. As I am not having anything on this side, so I am concentrating on this side only. So anyway, if an RESB message is sent from R3 to R2 and suddenly R2 sees that no, on this side the bandwidth has gone down. I cannot ensure a bandwidth of 50 Mbps on this side. So immediately it sends a RESB error message, right? Immediately it sends a RESB error message to R3. So these are the error signaling messages. These are actually replied immediately, right? Because these are error messages. These are not path messages. Rather, these are not path constructing or path maintenance messages or path tear down messages. These are error messages which need to be conveyed very quickly, right? So these are directly replied back. Now let us discuss these RSVP messages. Let us discuss some of their properties. These are very simple properties. So the messages that we have come across till now is path, RESV, path error message, RESV error message, path tier, reservation tier conf, and hello message, right? Hello message definitely should be there because RSVP neighbors, because if you consider these two routers, they will also be RSVP neighbors. So RSVP neighbors should be exchanging hello messages between them. First of all, they should be RSVP neighbors, isn't it? Because if you haven't configured RSVP in the middle router and you have configured RSVP here and you have configured RSVP here, then how come this path will be created by RSVP, isn't it? So first of all, they should become RSVP neighbors, and then they will be able to create a path using RSVP. Now this RSVP neighborhood is actually created and maintained by using periodic hello messages. This is exactly similar to OSPF hello and EIGRP hello messages. So now these messages have their message types. These are actually already specified. We don't have to do anything with these. So path message is a type 1 message. In fact, if you are checking the log messages, RSVP log messages in your routers, then you will see that these messages will be numbered by certain numbers. So these numbers, they indicate the type of the message. So if it is a path message, it is a type 1 message. If it is RESV message, type 2 message, and so on. Now direction. The path message is always a downstream message. RESV upstream, path R is upstream, RESV R is downstream, path tier is again downstream, RESV tier is upstream, RESV tier conf is downstream and upstream, and hello is always upstream and downstream. What do you mean by upstream and downstream? Simple concept. From head end to tail end is downstream, and from tail end to head end is upstream, right? So from head to tail is downstream. That is in my diagram, if you consider it from left to right, it is a downstream process, and from right to left is a upstream process. Forget about left and right, just remember that from head to tail is downstream, from tail to head is upstream. Now this path message, we have already seen this path message, this RESV error message, path tier message, RESV tier conf, and hello message. All these messages, they will definitely go from upstream to from the head to the tail, right? So definitely they are downstream messages. At the same time, RESV message, path error message, then RESV tier message, and hello message, they can move, or rather they will move uh, from the tail to the head. So they are all upstream message. If you are following these upstream and downstream directions, you can very easily understand the destination also. Downstream messages have tail as their destination. The upstream messages, they have the destination as the p hop. or the previous hop, right? The path error message, its destination is P hop or the previous hop. Reservation error message is the N hop or the next hop. Path TR message once again is directed entirely for the tail. RESV TR message for the P hop. RESV TR confirm message N hop and hello P hop and N hop. Let me just explain it with respect to this diagram. If you consider this path message. So path message is directly carried forward, right? From R1 to R5, it is directly carried forward. So it is directly targeted for the tail, right? It is a downstream message and it is directly targeted for the tail. Understood? Whereas if you consider the RESV messages, the RESV messages are sent to the previous hops. So this RESV message is received here. This RESV message is not this one, right? It is the RESV message generated by R4. This RESV message is that one generated by R3, not this one. So all these RESV messages are distinct and different RESV messages, right? Whereas if you consider this path message, it is that same path message that is propagated from R1 to R2 to R3 to R4 to R5. So this path message is same as this, same as this, same as this. The in-between routers R2, R3 and R4, they haven't done anything. They haven't generated their own path messages, right? They have simply forwarded the path message which has been sent to them by R1 unchanged ultimately to R5, right? So that's why it is directly targeted for the tail end, whereas these RESV messages, these are targeted for the previous hops, right? In this way, I hope you can understand. Once again, if you go for this path tier message, the path tier message is the same throughout. But this reservation tier messages, these are different, right? One by one, they are tiering their reservation and they are sending back their individual reservation tier messages to the previous hop, right? Now, something to tell here also. So router alert, here we have another column, router alert or RA in short. Now, here you can see a very simple fact, that is all the messages which are the same message that is directly targeted for the tail, they only have this router alert property, right? The remaining messages, they do not have any router alert property. So what is this router alert? Router alert or RA is a signal to tell every hop in the path must look into the packet, right? To be noted, all messages with RA are downstream, yes, because path and path tier, these are all downstream messages. All messages with RA have the destination tunnel tail, yes, they do have the destination of tunnel tail. All messages without RA have the destination either previous hop or next hop. It is also very simple to observe, right? Okay, so we have completed all the three issues. We have completed all the three issues related to the path building. So at first, the IGP is the information gatherer for creating the path. It gathers information and hands those information to CSPF. CSPF is the design engineer who actually draws the blueprint for creating the path by specifying the explicit root objects. And then finally, Rsvp or the site engineer actually develops that path on the basis of those root objects and does the maintenance and management of that path, right? So whatever related to creation and maintenance of the path has been completed. Now we come across certain other issues related to the MPLS TE path. Now this is one issue. What is the cost of the TE path? Definitely it is a path, so it should be having a cost, right? By default, the TE path is the IGP shortest cost to go to the tail end of the path. Cost of any destination behind the tunnel is equals to the TE path cost plus the cost between the tail end and the destination. If we need to specify the TE path cost manually, it should be done inside the tunnel configuration with the auto route configuration statement. We have already come across this auto route statement beforehand when we are actually advertising, when we need our IGP to advertise the tunnel interfaces into their routing tables. So here once again we are coming with that auto route statement. Now what about the TE path cost? The TE path cost, it is telling that it is the IGP shortest cost to go to the tail end of the path, obviously, right? Because just remember, this path has been created after a lot of considerations and consultations, right? Consideration and consultation between whom? Between our IGP, between CSPF, and then Rsvp, right? And the main consideration is whether I have the available bandwidth, right? And if you are ensuring that bandwidth issue, obviously you should be going for a path which is having the lowest cost. Because if you are focusing on a path which has a higher cost, then definitely you will come up with issues with lower bandwidths, right? And maybe in that case your desired bandwidth will not be able to match according to the path bandwidth. So it is obvious that the tunnel path bandwidth will be always the lowest IGP cost. And if you want to specify a manual bandwidth, you can specify it with the auto route statement, right? And what about the cost which lies beyond the tail? If there are certain destinations which are beyond R5. So in that case, you will see that the total cost will be this cost plus the other cost. It is a very simple logic. Now, auto bandwidth. Very interesting issue, auto bandwidth. This is a method by which the traffic rate in a TE path is monitored periodically, and accordingly the path bandwidth is resized to fit the traffic size suitably. It is configured by the auto BW method in the tunnel configuration mode. Now, what is this auto BW or auto bandwidth? See, I have specified, say, a 200 Mbps bandwidth for Rsvp, right? And Rsvp has prepared that path with a 200 Mbps assurance. After that, we see that the data that we are sending through this path, they are seldom crossing 100 Mbps size, right? So in that case, there is no need to maintain an operational, fully functional 200 Mbps path. And it will be very, very nice if that path can automatically expand or shrink itself according to the data volume that it is letting through it, right? So if we are not specifying this auto BW method, then our path bandwidth will be always a fixed bandwidth. But if we want to have a economic use of our path bandwidth, then definitely we should be working with auto BW. Now auto BW how does it get the intelligence that how does RSVP understands that and the entire process understands that yes, now I need to shrink the path, or yes, now the time has come when I need to expand the path. How come this intelligence can come in that situation? Now that intelligence is due to these 5 factors. What are these 5 factors? Application frequency, in short, that is capital A; tunnel bandwidth, capital B; collection frequency, capital C; highest collected bandwidth, capital H; and delta, or capital D. What are these? Application frequency, its default period is 86400 seconds. That means the entire day. It specifies how frequently the TE path traffic bandwidth requirement varies. Right. So, how frequently the traffic bandwidth varies? The traffic bandwidth requirement varies. Right now, I am having a bandwidth requirement of say 150 Mbps. Then after say 1 minute, I have a traffic bandwidth requirement of only 75 Mbps. Then again after 1 minute, I have a traffic bandwidth requirement of say 100 Mbps. So that means this 1 minute interval is actually the frequency uh, as to uh, how my traffic bandwidth requirement is modifying according to the requirement. Tunnel bandwidth, by default this is 0 kbps, specifies the value of configured bandwidth for the TE path. Right. So this is basically the bandwidth that should be allotted for the tunnel. Collection frequency, default is 300 seconds, specified, that means 5 minutes, specifies how frequently the TE path bandwidth is polled. Right. Now there must be a mechanism. A little while ago I was raising a question as to how come an intelligence is imparted into the system, that yes, my bandwidth requirement has become low, so I need to shrink the path. Yes, my bandwidth requirement has gone high, so I need to expand the path. So how this kind of an intelligence is imparted? So that intelligence can be imparted if the path is under observation or polling, right? So the interval after which the path gets observed by RSVP, obviously, that interval is called the collection frequency. So if RSVP is monitoring or polling that entire path after say 1 minute, so that means after every 1 minute RSVP is monitoring it, right? If I am putting there 10 minutes, then RSVP will be monitoring it, right? Now once again, don't confuse these with this area, path maintenance, right? This path maintenance is entirely done by RSVP on its own. We need not be configuring any auto BW or anything method like that, right? So this is an inbuilt method for RSVP. But if we are configuring the auto BW method, then these defaults will be overridden, and the values that we specify in auto bandwidth will now come into action, right? So this collection frequency is actually how frequently or after which time interval RSVP will poll or monitor the entire path, whether it is what is its condition, right? And this polling is not for in case of path maintenance, it was actually a issue of whether the path is available or not, right? Because if you once again visit here, 4 outstanding path messages will be considered as a reservation to be down. So here, if the path messages are becoming outstanding. So that means the path is gone. But this polling issue, it is not for checking whether the path is available or not. It is for checking the bandwidth requirement for the path, right? Bandwidth requirement for the path. Highest collected bandwidth, or H, specifies the highest recorded bandwidth consumed by the TE path in the last A time. That means during this application frequency interval, what is the maximum volume of data that has traversed that path? So that is highest collected bandwidth. Finally, delta, which is highest collected bandwidth minus the tunnel bandwidth. It specifies the difference between highest recorded or consumed bandwidth and the configured bandwidth for the TE path. Now this can be even a positive value or a negative value, right? Mind this delta can be a positive or a negative value. Why? Because this H can be higher than this B or lesser than this B. Under normal situation, highest collected bandwidth as per our expectation must be always below the tunnel bandwidth, right, as specified in auto VW method. But if it is exceeding the tunnel bandwidth, in that case the delta will give a negative value, because in that case, if it is exceeding the tunnel bandwidth value, then this delta will become a positive value. Because if the tunnel bandwidth has been specified as 100 and the highest collected bandwidth has been observed to be say 150, so definitely H minus B will give you a positive value. And if the H value is less than this B, then H minus B will be always a negative value. If the reverse happens, that is, we have specified a tunnel bandwidth as 100 Mbps and we have observed that the maximum or highest collected bandwidth is only 75 Mbps, then 75 minus 100, that means minus 25 will be the delta value, right? Now, what is the working principle logic of auto bandwidth? These are the parameters. So how this auto BW method will be working? When the T path is first configured, then the timer A is started. So timer A starts. The application frequency starts. And after C seconds, the D is calculated. So let the application frequency be 1 hour, right? And the collection frequency is 5 minutes. That means the entire change of bandwidth happens during 1 hour. The entire ups and downs of the bandwidth, it happens during 1 hour. And inside this 1 hour, I am polling. That means I am observing the bandwidth condition of my tunnel after every 5 minutes, right? And after every 5 minutes, I am calculating the delta. That is H minus B value. After A expires, that means after the entire 1 hour gets complete, the value of this bandwidth is B plus D or B minus D, right? When we have to do a B plus D, see, B plus D means we need to increase the bandwidth. So when this will happen? This will definitely happen when delta will give you a positive value. When delta will give you a positive value? When the highest collected bandwidth gets higher than this B, right? So when the highest collected bandwidth becomes higher than the tunnel bandwidth, then it is definite that I need to increase the tunnel bandwidth. So for that reason, the tunnel bandwidth is incremented by the delta value. And the delta value is definitely a positive one. Now, if the highest collected bandwidth is lesser than the tunnel bandwidth, then the delta value or H minus B will be always negative. So when we are subtracting B minus D, we are actually shrinking. We are shrinking the tunnel bandwidth. Why? Because we have seen that we don't need so much of bandwidth, because the highest collected bandwidth is lower than the actual tunnel bandwidth. So the amount by which it is lower, we have shrunk the tunnel by that amount. If the highest collected bandwidth is 75 Mbps, if the tunnel bandwidth is 100 Mbps, in that case your delta will be minus 25. So what we will do? We will go for B minus D, right? That is, the tunnel bandwidth is already 100 Mbps, so we subtract 25 from it and we settle it at 75 Mbps, because we have seen that the data is consuming maximum 75 Mbps, not more than that, right? Once again, after certain time intervals, after these polling intervals, we come across a situation that no, we have now done that, we have specified the tunnel bandwidth, or rather Auto BW has specified the tunnel bandwidth to be 75 Mbps, and at sudden bursts the highest collected bandwidth is becoming 100 Mbps. That means higher than this tunnel bandwidth. Now in that case, H minus B will give you a positive value. 100 minus 75, that is plus 25. So when that is added to this bandwidth value, or B plus D, that means now due to auto bandwidth, the tunnel bandwidth has been shrink to 75 Mbps. Now we need to once again add extra 25 Mbps, because the data are coming in that chunks. So once again the tunnel is expanded up to 100 Mbps. So in this way the auto bandwidth method works. Very interesting method, very intelligent method. Now the load sharing between the TE path and the IGP path, right? Because you see, till now we haven't discussed anything regarding the load sharing. And when we started with our MPLS TE chapter today, we have discussed, we have expressed this fact that our desire to perform a traffic engineering is a load sharing. That is to use the underutilized path, right? So we haven't done anything by which we can show something that we are using the underutilized path also. So now we are coming to that situation. Now you can have two types of situations. Either you can have your original IGP path and your TE path, or you can have two TE paths, right? Once again I repeat, you can have your original IGP path and your TE path, or you can have two TE paths. And in both cases you want to do a load sharing. That means in the previous case you need a load sharing between the IGP path and the two TE paths, and the TE path. And in the second situation, you need to load share between two TE paths. So how it is done? It has some rules as follows. No load sharing if the destination is the TE path tail, right? So that means if I am using IGP and a TE path, or if I am using two TE paths, and if my destination is just the tunnel endpoint, not something beyond that, right? So let us come to this figure. So let us assume that this is an IGP path and this is MPLS path, and we need to our destination is just the tunnel endpoint. In that case, no load sharing, right? It will always follow the path which has the least cost. If your TE path has the least cost, then it will be followed. If your IGP path has the least cost, it will be followed. And even if these two are TE paths, both, no IGP path, then also if the destination is just the tunnel tail end, then no load sharing happens. Only one particular path will be used. Now for destinations beyond the endpoint. So load sharing is allowed if the destination is behind the TE path tail, and it is always equal cost load sharing. Unequal cost load sharing can be done between two or more TE paths, provided they all have non-zero bandwidth. Otherwise, it is always equal cost load sharing. Right. Now, once again, this is an IGP path, this is an MPLS TE path, and we need to, our destination is somewhere beyond this tail end router, right? Now, in that case, it will be a load sharing and obviously equal cost load sharing. Why equal cost load sharing? Just be careful about this fact that we are using an IGP here and a MPLS TE path here. Now, IGP will by default use its least cost path, isn't it? And MPLS TE path, its cost will be also the least cost, IGP least cost. We have just discussed it a little while ago. If we have specified some manual cost for the MPLS TE path using autoroute, then it's a separate story, right? But if we are not doing that, in that case, the MPLS TE path has the same cost as the IGP least cost path, right? So in that case, both these two paths will be doing an equal cost load sharing. You can achieve unequal cost load sharing if both these two paths are MPLS TE paths, not IGP path, right? And by using that auto route method, you have configured different costs. You have configured a cost here, say for example 10, and here 20. For this path the cost is 10, for this path the cost is 20. In that case, you can, as this is having a lower cost, then you can expect a higher proportion of bandwidth, a higher proportion of data to be traveling through it, and a lower proportion of data to be traveling through it. And you can have an unequal cost load sharing, right? So once again, in a nutshell, if you are using IGP and MPLS TE path, forget about any kind of unequal cost load sharing, right? It will be equal cost load sharing. Why? Because by default, the MPLS TE path cost will be the least cost IGP path, right? So it will be a equal cost load sharing. Only if we specify an auto route cost value for this MPLS TE path, then definitely this IGP path will be followed, because IGP will be getting the priority, right? But if both these are MPLS TE paths, in that case, you can achieve an unequal cost load sharing if you have specified their specific costs by using that auto route method. Is it okay? Now we come to the very last issue of this traffic engineering part, and that is fast reroute or FRR. Very interesting issue. This is a protection method for a particular TE path. It ensures minimal loss or traffic upon failure. The backup path or protection path for primary TE path is pre-established before any failure happens. It is to be noted separate independent TE paths for primary TE path can be signaled only after primary TE path fails, right? Once again, back to this diagram. Here, suppose this green and blue, these are two TE paths. Why we have made two TE paths? Because we want to maintain this TE path as a backup, right? So this should be our primary TE path and this should be the backup TE path. Okay. Now, this backup TE path will be available only after this present TE path fails or the primary TE path fails, right? It will take up certain activation of Rsvp and certain redirection of traffic once again. So you cannot consider a backup path as a protection measure for an existing path. And backup path is always a backup path. It's not a protection issue, right? And see, if you want to make a backup path, it will be an end-to-end path also. So that means if you want to maintain a backup path, you have to maintain at least two end-to-end paths, right? So there are two issues in maintaining backup paths. First issue is backup path is not very prompt in action. When the primary path fails, after the exchange of all the RSVP messages and everything is done, then only the backup path gets activated. So this is number one issue. And number two issue is if you want to maintain a backup path, you have to maintain it as long as the primary path, right? But you can very easily give protection to your single MPLS TE path without maintaining any backup path. How this can be done? This can be done by the first reroute method or FRR. So let us see how it is accomplished. Now, TE path protection can be of two types. Path protection, end-to-end protection of the primary TE path. It is not supported in Cisco. It is exactly similar as a backup path, right? Where you have to go for the protection end-to-end. So in case of Cisco, Cisco doesn't encourage it. And if you are doing it in a Cisco router, you have to just maintain a backup path. Nothing more than that. Local protection is appreciated and encouraged for the Cisco, and this is a much grand solution, a much better solution instead of maintaining a path protection. Now the local protection, backup TE path is built to cover only a segment of the primary TE path, and it is routed around a failed link, which is called the link protection by n-hop backup path, or node, that is failed node, which is called node protection by next to next hop or nn-hop backup path. Now here we come across certain initials. So let us discuss those initials at first. So some related terms are point of local repair or PLR, that is the head end of the backup TE path, merge point MP, tail end of the backup TE path, n-hop, next hop from the PLR, nn-hop, next to next hop from the PLR. It is to be noted that TE path failure can be detected by SONET alarms or RSVP hello mechanism. Okay. So let us come across two situations. These are the two situations. Now here we have this green curved line. It represents an MPLS TE path from R1 to R5, right? Now between R2 and R3 we maintain two links, right? One link will be carrying the functional TE path, whereas the other link will be carrying the protection path, right? Now how is it done? Whenever this particular link fails, so we consider it as a failed link, immediately in range of milliseconds interval, such a small interval, immediately the next link starts to work. So there is no hiccups, no stoppage or no cramming of data here. Now we come across these definitions PLR and MP. So PLR, or point of local repair, is that particular point where actually the repair needs to be done. That means the protection path where it will start, and MP or merge point is that point where the protection path and the original path will get reunited, right? So PLR is actually that point where the protection path, right, where the protection path will start, and MP is that point where the protection path and the original path gets united, right? So this kind of a path protection is called link protection by using n-hop. N-hop means next hop. Why using n-hop? Because here this R2 is utilizing R3, who is the next hop router, right? Who is the next hop router. So this particular link has failed. For that reason, the entire green MPLS T path has become non-functional. Within a fraction of a second, this combination of green and blue path comes up, right? And this green and blue path is established by the next link, which is connected to the next hop. That's why this is link protection using the next hop, right? Link protection, you are protecting this link using your next hop router. That means your point of local repair, your merge point lies in your next hop router, right? You are not going beyond it. Now if you see this diagram where you are maintaining a direct connection from R2 to R4. Now in this case, if R3 fails, these two links will definitely fail, right? And even if you maintain additional links between R2 and R3, as R3 has altogether failed, that means the router has become faulty. In that case, no use of maintaining multiple links between R2 and R3. So this is not a question of link protection. This is actually a question of node protection, because the node has become faulty. So whenever that node becomes faulty, this green MPLS T path becomes non-functional. And within a split, within fraction of a second, within milliseconds interval, this combination of blue-green MPLS T path comes up. Now this blue portion of this T path, it has its MP or merge point at the next to next hop router, right? That's why it is called a node protection by next to next hop. Why this is a next to next hop or NN hop? Because the MP is connected to the next to next hop. R4 is not the immediate next hop for R2. It is actually the next to next hop for R2, right? Whereas in the previous case, R3 was the next hop for R2, and the merge point or MP was present at R3. So that's why it was a link protection by N hop. And in this situation, it is a node protection by next to next hop, right? I hope these things are clear, and we'll be, whatever theory we have done today, we'll be doing practical on all these topologies, right? On all these topologies, we'll be seeing how we are developing the MPLS T path, how we can maintain backup paths, how we can go for this link protection and node protection, and we can arrange for path protection, right? So that's all for this MPLS theoretical session. It has been a very long session, right? Because I had to discuss a lot of things. Why a lot of things? Because I have already discussed that, and I think now you people have already realized this fact, that why I had to do this very long discussion, because we had to come across some very new concepts which with which you may not be familiar with. And so for that reason it has become a very detailed lecture. So thank you so much for your cooperation and your patience, and I definitely hope to see you all in my next class, where I'll be starting with the practical of these MPLST. So that's all. Bye for right now. See you again for the next class. Thank you so much.